Namaste and a very good morning to all of you. I welcome you to my channel, The Outlier. In today's presentation, we'll be looking at one-way analysis of variance. One-way analysis of variance is used when you want to compare three or more than three groups. And secondly, there is an important assumption called as the homogeneity of variance assumption. Now, you have to look at the prerequisite for one-way analysis of variance, which is to check whether the homogeneity of variance assumption is satisfied or not. Now, to demonstrate one-way analysis of variance, I will be using a data set which is called as the breaks data set. Let me demonstrate one-way analysis of variance in SPSS. As you can see, I'm using SPSS. Let me click on the option File. The second option here is Open. And within this, the very first item is Data. There are different data sets that are being shown here. I will use the option breaks.sav. This is the file which I will be using to demonstrate one-way analysis of variance. Let me click on the option Open. Right. As you can see here, I've got two important variables. The first one is the machine, and there are 8 sets of machines. As you scroll down, you can see different sets of machines that are being shown here. The second variable here is the disk break diameter. I repeat, it is the disk break diameter of the first machine. Here, the disk break diameter is 322.0003 millimeter. The second one would be 322.0048. One of the first things that I need to do here is the variable machine is being shown as a scale variable. The first variable machine is not a scale variable, it is a nominal variable, and therefore I need to change the data type to nominal. To change the data type to nominal, what I'll do is I'll go to variable view. This is the variable machine. As I scroll to the right side, what you'll be seeing here is what is called as measure. It shows scale. You have to click on the end of the cell, and in the drop-down menu, please choose the last option, nominal. Now, SPSS will read the variable machine as a nominal variable. I'm still in the variable view. Let me switch to the data view. As you can see here, the icon changes. This is the icon that you see for a nominal variable. I have 8 sets of machines, and for each of these 8 sets of machines, disk break diameter is measured. Now, the question here is whether the disk break diameter produced by these 8 groups of machines, is it the same or is it different? Now, when we have to compare the mean values for more than 3 groups, we use one-way analysis of variance. We can't use independent samples t-test. To execute the one-way analysis of variance, what I will be doing is I will click on the Analyze menu. Here you see different options. Let me choose the option Compare Means. You can see here there is an option which is called as Compare Means. Once you enter Compare Means, it shows 6 different options. I will be choosing the last option, namely one-way analysis of variance. So this is the navigation path. Please go to the Analyze menu. And within the Analyze menu, you'll have to choose the 5th option, namely Compare Means. Within Compare Means, you are displayed 6 different options. Please choose the 6th option, that is one-way analysis of variance. This is going to be in 2 parts. In the first part, what I will do is I will be doing the exploratory data analysis for one-way analysis of variance, and then we can look at the results of one-way analysis of variance. As you can see here, the machine number is a factor variable, and therefore I will be choosing this in the factor list. When you look at the disk break diameter, this will be pushed into the dependent list. I'm interested in checking whether the average disk break diameter is the same for these 8 sets of machines or different. Now, you see a whole lot of options like contrast, post hoc options, and bootstrap. I will ignore some of these options and head straight to the options tab. Let us look at the preliminary analysis. Here, I will be doing the means plot, and you can see here, homogeneity of variance test. Let me draw your attention to a couple of important points here. When we work on one-way analysis of variance makes two important assumptions. Anova says that the dependent variable should follow normality. I repeat, the dependent variable should follow normality. Why? This is a typical example of a parametric test. And in parametric tests, there are certain distributional assumptions. The dependent variable has to follow normality. Having said that, we do not check for the assumption of normality here. You may ask me why. The simple answer is Anova is robust to the violation of normality. I repeat, Anova is robust to the violation of normality, and hence I do not have to check for the assumption of normality within Anova. The second assumption that Anova makes is homogeneity of variance test. This is a very, very important assumption. We must check homogeneity of variance assumption. Only when the variances are the same or homogeneous, then and only then we can look at the results of one-way analysis of variance, and we can consider the output of one-way analysis of variance as reliable. Else, we cannot look at the one-way analysis of variance output. The results of Anova will not be reliable. If the homogeneity of variance test fails, you cannot look at one-way analysis of variance. What you have to do is you have to look at an alternative test, which is called as Kruskal-Wallis Test. I repeat, you'll have to look at the non-parametric alternative, which is called as the Kruskal-Wallis Test. So this is the deal. Please check for please check for homogeneity of variance test. If the results say, yes, there is homogeneity of variance in your data, that is, the homogeneity of variance assumption is satisfied, you can proceed to look at the output of one-way analysis of variance. If the homogeneity of variance test fails, then we do not look at the output of one-way analysis of variance. The alternative, the non-parametric alternative for one-way analysis of variance is Kruskal-Wallis test. We have to proceed to Kruskal-Wallis test if the homogeneity of variance criteria is not satisfied. So this becomes a very, very important test, that is homogeneity of variance assumption. I cannot emphasize the importance of homogeneity of variance test enough. So I have clicked on homogeneity of variance assumption. I have also clicked on the means plot. Let me choose the option continue and then say OK. As you can see here, there are three different outputs that it is producing. Right at the beginning, you are able to see test of homogeneity of variances. So it produces 4 different tests. I'm more interested in the test based on the means. We will be looking at what is called as Levin's statistic. So Levin's statistic is used to test whether homogeneity of variance assumption is satisfied or not. So this is the degrees of freedom for the first variable. This would be the degrees of freedom for the second variable. So if you have 8 groups here, 8 minus 1 is 7. And therefore, it is displaying 7 as the degrees of freedom for the first variable. And for the second variable, the degrees of freedom would be 120. What I'm really interested in is this number 0.616. Remember that this is the p-value. P-value helps you decide whether homogeneity of variance assumption is satisfied or not. Since the p-value is greater than 0.05. I repeat, since the p-value is greater than 0.05, we can go ahead and accept, or in other words, we do not reject our null hypothesis and conclude that homogeneity of variance assumption is satisfied. I will repeat this. Please look at this. We are looking at the Levin statistic to check whether the homogeneity of variance assumption is satisfied or not. The p-value that I have obtained is 0.616, which is greater than 0.05. Since the p-value is bigger than 0.05, we go ahead and say that the homogeneity of variance assumption is satisfied. So what you may ask me, If the homogeneity of variance assumption is satisfied, then the second table would make sense. If for some reason the p-value is less than 0.05, imagine that tomorrow you're picking up another data set and checking for the homogeneity of variance assumption. If the p-value in your case is smaller than 0.05, then you would reject the null hypothesis and conclude that homogeneity of variance assumption fails, in which case the second table would be redundant, it would be useless, it would be unreliable, and you will not proceed to look at the results of ANOVA. In my case, the p-value that I have obtained is 0.616, which is greater than 0.05, and therefore the homogeneity of variance assumption is satisfied. I can proceed to look at the results of ANOVA. Even before I interpret the results of ANOVA, let me scroll down and show you the graph. In the x-axis, what you see here is that you have the machine number. There are 8 sets of machines that you are able to see here, 1 all the way up to 8. And in the y-axis, you can see it has plotted the average disk break diameter, which is measured in millimeter. So if you can see here, the average disk break diameter for the first machine is less than 322. But when you look at machine 2, it is on the higher side. And it looks very, very different as compared to the rest of the groups. Let's take a look at the third group. For the third group, it is less than 322 millimeter. For the fourth group, it is further less than 322 millimeter. Let's look at the fifth group. It is on the higher side, it is greater than 322 millimeter. For the sixth, it is again greater. For the seventh, it is greater than 322 millimeter. And for the eighth group, the average disk break diameter is less than 322 millimeter. So this is what is called as the means plot. So this gives you an idea about what is the average disk break diameter for the 8 sets of the machines. Now, let me proceed to the ANOVA table. This is what we are most interested in. You see, there are 3 breakups here. One is the between group sum of squares. The second one is within group sum of squares. And this is the total sum of squares. Now, the best way to understand is when I say between groups, what I'm trying to say is you have 8 different sets of machines. Between the first and the second, you can have a difference. Between the second and the third, you can have, between the second set of machines and the third set of machines, you can again see some difference. Like this, between the groups, you can see difference. The same way, just as you have between groups variability, you can have variability within the first set of machines itself. You can have variability within the second group of machines itself, so on and so forth. So the between groups of squares captures the difference between the groups, and the within groups variability, within group sum of squares captures the variability within the groups. You have the degrees of freedom. We have already seen the degrees of freedom. If you take 0.004 and divide it by 7, you'd be getting the mean square. So between group sum of squares divided by its degrees of freedom will be giving you the mean square for between groups. Similarly, for within group sum of squares, when you divide it by the degrees of freedom, you'd be getting the mean square for within the groups. When you take the ratio of the mean squares, you'd be getting the F statistic, which is 7 in this case. And finally, you have the significance value, which is reported for the F statistic here. What can I see when I look at the significance value? Since the significance value is 0.000, it is clearly less than 0.05. Since the significance value is less than 0.05, I can go ahead and conclude that there is the significant difference in the average disk break diameter for these 8 sets of machines. I'll repeat, since the p-value is less than 0.05, I will reject my null hypothesis and conclude that on an average, the disk break diameter produced by these machines is different. Or if I have to be more formal, I will say there is at least one group, I repeat, there is at least one group which has a significant disk break diameter as compared to the others. Now, one question which pops up in our mind is, which is that one group which has a significantly different disk break diameter? Which is that one or more than one group which has significantly different disk break diameter? To answer this question, whenever you reject the null hypothesis in ANOVA, the way I have rejected in this case, what you do is you can proceed further. Now, this is the second stage of our analysis. We are investigating which is that one group or more than one group which has a significantly different disk break diameter. To answer this question, we propose what is called as post-hoc tests. The word post-hoc is a Latin word. You might have heard of the word ad hoc, which means temporary. The word post-hoc means after this what, right? After rejecting the null hypothesis in ANOVA, how do we proceed from here? We have to do a post-hoc test to identify which is that disk break diameter, which is that machine which is causing my null hypothesis to be rejected here. To do this, what I will do is I will go back to ANOVA. Let me go back to the data set. So this is my breaks data set. Now, at this stage, I will go to graphs. You see a whole lot of options here when it comes to graphs. I will choose the option chart builder. Now you have machine number and disk break diameter. I will select both of these variables. I don't have to choose chart builder. I'm sorry, this is the wrong option which I choose. So let me just click on the option cancel. And what I will do here is I will choose the option graphs. The second option here is what I need to choose. Earlier, I chose the first option chart builder. I'm not interested in chart builder. I can choose the second option here, graph board template chooser. Let me choose the graph board template chooser. As you can see here, there are two variables that it is showing, machine number and the disk break diameter. So it shows that these are all some of the appropriate graphs that I can draw for my data set. I will choose the option box plot. I repeat, I will choose the option box plot. X-axis here will be the machine number and the y-axis here would be the disk break diameter. I can make certain changes here. Let me go to the option detailed, and to the right hand side you see the option color. Let me click on the option drop down menu. Once I click on the drop down menu, I can choose machine number. So I will be able to see 8 different colors for 8 different sets of machines. So when it comes to the basic tab, I've chosen the box plot. When it comes to the detailed tab, what I've done here is under the color section, I've chosen machine number. Let me choose the option OK. Right? In the output window, what you will be able to see is the box plots. You can see here, there are 8 different sets of machines. I repeat, there are 8 different sets of machines in the x-axis. The disk break diameter for each of these 8 different sets of machines is being shown. You can also see the legend here corresponding to each of the 8 machines here. What do I see here? Right at the top, for the second machine, the average disk break diameter, the thick line that you see here, which cuts the box plot, represents the median, which means that the median disk break diameter for machine 2 seems very, very different as compared to the others. If you roughly take 322 as the benchmark, the first machine, similarly the third machine, and to some extent the 5th and the 6th machine all have an average disk break diameter which is close to 322. Let me just repeat this for you. The first set of machines, the third one, and the 5th and the 6th one, all of these have the average disk break diameter which is close to 322. When I look at the machine 2, it has an average disk break diameter which is very, very different from the others. So this is something which is very, very interesting, and I would like to investigate this further. Now, are these differences real or not? I repeat, are these differences real or not? To answer this question, what you will have to do is you will have to go back to one-way analysis of variance. Let me click on the data editor window. This is the analyze menu. I can click on compare means, and as before, I will be doing one-way Anova. We have to do the post hoc test to check which is that one machine or more than one machine which has a different disk break diameter. So right at the top, you can see the option post hoc. This is right below contrast. So this is the second tab here, post hoc. The moment you click on this, you can see a wide variety of options that SPSS provides. You can see it is highlighting in blue, equal variances assumed. And you can see there are at least 10 to 15 different options under equal variances assumed. Popularly, people use LSD or Tukey's test. When you do not assume equal variances, you have Dunnett's test or Games-Howell test. You also have different options here, but most popularly people use either the Dunnett's test or Games-Howell test. Now, we have seen in the null hypothesis that equal variances assumption is satisfied in my data set. And therefore, I will be choosing the Tukey's option here to do the post hoc test. As you can see here, this is post hoc multiple comparisons. So I have chosen the Tukey's test. In simple language, if you have to understand post hoc tests, just remember one sentence. It is doing a pairwise comparison. I repeat, it is doing a pairwise comparison for each pair of the 8 machines in the data set. Let me click on the option continue and choose OK. We are familiar with the homogeneity of variance assumption. We have looked at Anova. Now, as I scroll down, you can see here, you are able to see the post hoc test. This is the heading, post hoc test. It is doing multiple comparisons. Now look at this, machine number 1. So here in the first set, you are comparing the first set of machines with the remaining 7 set of machines. And wherever you're seeing an asterisk mark here, it means that the mean difference is significant. You're comparing the first set of machines with the second group. Similarly, the first set of machines are compared with the third, fourth, fifth, sixth, seventh, eighth, respectively. And for each of this pair, what is the mean difference is being highlighted. And wherever you see an asterisk mark, it means that the pair has there is a significant difference in the means for each of this pair. For example, when you compare the first set of machines with the second set of machines, you see there's a mean difference of 0.05. There's a negative minus 0.05 value that is being displayed, and it also shows a star mark, asterisk mark, indicating that the average disk break diameter for the first set of machines and the second set of machines is significantly different from one another. You can also look at the p-value. The p-value is less than 0.05. I repeat, the p-value, which is 0.000, is less than 0.05. Since the p-value is less than 0.05, I will reject my null hypothesis and conclude that there is a significant difference in the average disk break diameter between the first set of machines and the second set of machines. You can see the 95% confidence interval, that is the lower bound and the upper bound, that is reported for the mean difference. Like this, you can see for each machine, it is comparing with the remaining 7 sets. Now, one interesting thing that you can see here is there are subsets of machines that it has been able to make as the next table. You can see what is called as homogeneous subsets. Now, very interestingly, there are 3 groups of machines that Tukey's test is reporting. This is the first group of machines in the column. This is the second set of machines, and this is the third set of machines that it is reporting. Now, in the first group of machines, it has classified machine number 48316 and it has put it in one group. It has put it in one group because by and large their average disk break diameter is very, very close. In the second group, it has classified machine 8, 3, 1, 6, 5, and 7. Similarly, it has made the third group. You can see here, it is slightly above 322 here. The average disk break diameter, which fall in the third bucket, is slightly above 322. So you have machine number 5, 7, and 2, which all belong to the third group. So when you look at these three groups, it is also reporting the p-value. The p-value is bigger than 0.05, which means that when you look at machine number 4, 8, 3, 1, 6, and 5, and compare their average disk break diameter, their average disk break diameter is almost the same, and the p-value is bigger than 0.05. That's how you can interpret for the subset 2 and 3 as well. This is the mean plot which we have already seen. To summarize the discussion that we have had today, we have looked at one-way analysis of variance. Two important points here. One is that you look at one-way analysis of variance when you want to compare 3 or more than 3 groups. This is the first important point that you need to keep in mind. Whenever you want to compare 3 or more than 3 groups, please use one-way analysis of variance. There is a very, very important assumption about ANOVA, that is homogeneity of variance assumption. And you must and should respect this particular assumption. That is, the homogeneity of variance assumption must be satisfied. Only if the homogeneity of variance assumption is satisfied, then and only then you can look at the results of ANOVA. If the results of homogeneity of variance assumption is not satisfied, I repeat, if the homogeneity of variance assumption is not satisfactory, what do? Please don't proceed to do ANOVA. You may ask me, what is the alternative? The non-parametric alternative for one-way analysis of variance is Kruskal-Wallis test. Now, to see how to perform Kruskal-Wallis test, please look at my other videos. I will be making videos for Kruskal-Wallis test separately. So this is very, very important, and the most important assumption as far as one-way analysis of variance is concerned, that is, you must respect the homogeneity of variance assumption. You don't need to look at the normality test because ANOVA is robust to the violation of normality. However, ANOVA is not robust to the violation of homogeneity of variance test. So please keep these points in mind. In case the homogeneity of variance assumption is satisfied, you have the license to look at ANOVA. And when you look at the results of ANOVA, in case you accept the null hypothesis for ANOVA, the matter ends there. On the other hand, if you reject the null hypothesis for ANOVA, you then go ahead and look at the post-hoc test, which is nothing but pairwise comparisons. So 3 points. The first point that you need to keep in mind is, please test whether the homogeneity of variance assumption is satisfied or not. Secondly, look at ANOVA. And thirdly, please proceed to do post-hoc tests. In this example, I've used Tukey's test. There are other tests which are available as well. With this, I've come to the end of today's presentation. I thank you very much for watching today's presentation. Have a good day. Thank you very much.